Hi everyone, this is Zhibo from Hong Kong University of Science and Technology. I'm going to give a presentation of our paper, How Far We Have Come, Testing Decompilation Correctness of C decompilers. This work was done with Professor Shuai Wang at Hong Kong UST. In this work, we made a comprehensive study on correctness of C decompilers and gave an up-to-date understanding of modern decompilers. Let me first introduce the background of our research. A decompiler takes binary code as input and outputs its corresponding source code. Science decompilers have been primarily used as the cornerstone of various cybersecurity and software reverse engineering missions. Its correctness is very important. There are already some successful business decompilers like AdaPro and JB3. They are probably the best decompilers we can get. And there are also some promising open source decompilers developed by reverse engineering community. All these decompilers are extensively used in various commercial and research applications. Although decompilation technologies have developed greatly in recent years, there are still some pessimistic views. Researchers tend to believe that decompilers are error-prone and prefer to use some clumsy binary hacking methods rather than directly using output of decompilers. So in this work, we want to give an up-to-date understanding of decompilation correctness. First of all, I will give an introduction of the structure of modern decompilers. Generally, decompiler consists of three main components: the front end, the middle stage, and the back end. In the front end, which marked in green, binary code will be translated into assembly code. Then the assembly code is lifted into an intermediate representation. All subsequent analysis will be performed on IR code, which is more analysis-friendly. In the middle stage, variables, types, and high-level program control flows are recovered from IR code. The IR code is also optimized at this stage. This stage is more complex, and it's considered to be the most challenging and important part in decompiler. In the backend part, the IR statements are translated into C statements. Translations are mostly maintained by concretizing code generation templates. So the motivation of this work is that academia lacks the latest understanding to decompilation results. Thus, we try to evaluate decompilers with clear metrics. More specifically, we wanted to answer three research questions. First, how difficult is it to recompile the outputs of modern C decompilers? Second, what are the characteristics of typical decompilers defects? And what insights can we deduce from analyzing the decompilation defects? In this work, we test four decompilers. AdaPro and JB3 are successful commercial decompilers. RedDec and the Gra decompiler plugin of Redar 2 are open source. Redar 2 is a popular reverse engineering framework. It has some decompilation plugins. The Gra plugin is one of the most mature plugins. Now I'll explain the methods we used in this study. The main idea of our research is to find the bugs with software testing, then analyze all bugs to answer research questions. But two challenges remain. First, how to effectively and systematically expose decompiler bugs. Since decompilers take executables as inputs, we need to generate them automatically. And second, how to verify the correctness of the decompilation result. We need to check the semantic consistency of the outputs, the C code. To solve the first problem, we leverage the famous SysMIS tool and the AMI testing method. SysMIS can generate random C programs. We take these random C programs as seed, then use EMI method to generate variants. I will give a brief introduction of EMI. This method comes from an idea: if we delete some statements that cannot be reached, behavior of the program does not change. For example, if we deleted printf in second branch, this program still has the same output. In other words, we have a test oracle. The program and its EMI variants have the same behaviors. So by deleting or inserting unreachable statements in a program, we can get a lot of EMI variants with same behaviors. As for the second challenge, to verify the correctness of the decompilation results, we try to recompile the decompiled code, then execute compiled binaries. However, our findings show that it is difficult to directly recompile the outputs of decompilers. To enable an automated workflow for testing, we seek to extract functions from the decompiled C code and use the decompiled functions to replace their corresponding code in the source code. The instrumented code can be recompiled into executable. In this study, we focus on three kinds of errors and defects. The decompilation errors are errors thrown by decompiler when processing input executable. The recompilation errors are yielded by compiler when we try to recompile the decompiled code. And the decompilation defect means deviant results of the recompiled executable and the input executable. So this is the workflow of our study. For each EMI variant, we first compile it into an executable. The decompiler will decompile this executable into C code. After that, we try to recompile the output of decompilers and get another executable. These two executables should have the same output, so we can check the correctness of decompilation by comparing outputs of executables. And once decompilation errors or defects are identified, we manually identify the root causes of errors. In the experiments, we generate 1,000 seed programs with SysMIS as seed files, then check the correctness of decompilation and mutate them with EMI method. After that, we check the decompilation results of EMI variants. Then finally, we analyze all incorrect results. Overall, more than 10,000 programs and variants are generated. It takes about 350 hours to examine our findings. There are some interesting findings. We can find lots of errors and defects in all 4 decompilers. More specifically, we found about 400 recompilation errors and about 1,000 decompilation defects. All discoveries have been reported to developers. We have also received some responses from developers. We're glad to know that our findings are helpful for developers to update software. Also, it's surprising to know that ISSTA also internally use SysMIS to test their decompiler. Here, I will give 3 examples of our findings. The first one is wrong variable type. We found that wrong variable types can even change the program execution flows. In this example, variable I is int type in the source code. but it's recognized as unsigned int type. If an unsigned int variable is compiled with a minus value, for example minus 12, this minus value will be converted to unsigned int. It will be a huge positive value. Thus, the value of this expression is true, and unreachable statements become reachable. Another example is about function call parameters. Function prototype recognition has been studied for a long time, but some decompilers still failed to recover correct function call parameters. This causes an inconsistency in the function declaration and the invocation of function. It can seriously prevent recompilation. And the third example is erroneous optimization. We found that decompilers usually use optimizations implemented by themselves, but some optimization strategies can be wrong in some cases. For example, in this case, on the left side, the variable 0 is an integer with 32 bits length. It's truncated to 8 bits integer in the second line. This truncation is considered superfluous and removed on the right side, because the variable 1 will be extended to 16 bits in the third line. So the optimization strategy will replace this truncation and extension with a single truncation. It's clearly wrong. Bit length is not correctly taken into consideration in this optimization. To analyze root causes of errors and defects, we also pinpoint buggy code fragments in 2 open source decompilers. Overall, we found 13 buggy code fragments. All of them are logical bugs. 12 of them are found from the middle stage, and the other one is from the backend. Finally, I will conclude our findings. To answer the first question, how difficult is it to recompile the outputs of modern C decompilers? Although researchers were generally believing that outputs of C decompilers are not for reuse and not even recompilable, our findings show that modern C decompilers already show good support of recompilation for many non-trivial C code. The results are promising when using decompilers in code reuse applications. The second question, what are the characteristics of typical decompilation defects? We found a type and the variable recovery failure occur frequently, although relevant techniques have been developed in academic for many years. And sometimes erroneous optimization can make decompiled code malfunctional. As for the third question, what insights can we deduce from analyzing the decompilation defects? We found that decompilers have not fully leveraged research outputs, and there is a mismatch between research articles and modern decompilers. Aggressive optimization in modern decompiler may hurt readability. As shown in this table, decompiled code becomes too concise. The average line of code of a function is 143, but the average length of outputs of decompilers is much shorter. Also, the similarity score of decompilers output is only about 0.5. At last, we have some suggestions. To developers, maybe more research results can be applied in modern decompilers. For example, academic researchers have proposed lots of variable and type recovery methods with promising results. Another thing is modern decompilers seem to go too far and hurt the readability of their outputs with aggressive optimization. Perhaps users should be allowed to decide the optimization levels of decompilers to improve readability. And to the academic community may consider to take the decompiled code for research instead of various functionality-preserving hacks. That's all of my presentation. Thanks.